Okay, in this lesson, we are going to take a more in-depth look at double displacement reactions, and we're specifically going to pay attention to what is happening to the ions in an ionic compound when they undergo double displacement. By looking at what is happening to these ions, what we are going to eventually be looking at in this lesson is total ionic and net ionic equations. Okay, so the focus here is to continue our conversations about double displacement reactions and being able to maybe think about if we could zoom in and look at what is happening at the level of the atom, and then writing and then communicating that in these total ionic and net ionic equations. So as we're going through our lesson today, you're going to want to hit pause and record what I have on my screen, copy that down into your notes. Okay, so we know from some previous learning that whether a double displacement reaction happens or not depends on the solubility of the product. So we know that in order for double displacement reaction to occur, we have to have two ionic soluble compounds to start, and then they switch partners, and one of those products has to be soluble or aqueous, and one of those products has to be insoluble or solid and make a precipitate. And so it's the fact that we can see that precipitate that tells us that a reaction happened. Okay. So we need to have an understanding that when you have an ionic compound, so we're going to look, actually, I'm going to backtrack. We're going to look at a double displacement reaction of sodium chloride aqueous, so sodium chloride dissolved in water, plus silver nitrate aqueous, so silver nitrate dissolved in water, reacting to produce sodium nitrate aqueous and silver chloride solid. So our precipitate, our insoluble substance, and our soluble substance. Now, when we look at sodium chloride, and we know that our sodium chloride is aqueous, and so this means that it's dissolved in water. Now, you know that sodium chloride or salt will dissolve in water. You can take a spoon of salt and you can stir it into a glass of water, and what you notice when you do that, the solid disappears and we don't see it anymore. The reason that happens is because we remember that our ionic compound is a sodium ion attracted to a chlorine ion like this. Now, in reality, there's a whole bunch of sodium ions and a whole bunch of chlorine ions bonded together to make that crystal of a salt that we see. Now, the sodium ion is positively charged, the chlorine ion is negatively charged, and they're attracted to each other. When you take a salt and you add it to water, what happens, for reasons we're not going to really talk about in this course, is that the ions separate. So the sodium ion and the chlorine ion get pulled apart, and they're both just floating around in the beaker or glass of water, not attached to anything. The same thing is going to happen in our bottle of silver nitrate. So if we take some silver nitrate and we stir it into some water, we originally have the silver and the nitrate ions attracted together. But once we add them to water, the ions separate. So we're going to pretend that we have some sodium chloride solution. So a solution, a bottle of sodium and chlorine ions floating around in water, and another bottle of silver ions and nitrate ions floating around together. So this is aqueous silver nitrate, and this is aqueous sodium chloride. If we were to mix these together, these two substances together, we're going to get something that looks like this. So in our solution, we're going to have a whole bunch of sodium ions, chlorine ions, silver ions, and nitrate ions floating around in solution. And I like to call this the ion party. What we know is that, going back to our particle theory, is that all the ions in this solution are moving around and colliding with each other. So just think about this for a minute. All of our ions are at an ion party. They're wandering around and mingling with each other. And when you're at a party, you tend to bump into people that you know. Okay. So we are going to pretend that we're going to pretend that our sodium ion and our chlorine ion collide at the party. Now, I would really like you to make sure that you are watching what I'm doing on my screen instead of just kind of half listening, half copying. So either hit pause and copy this down and then listen to the explanation, or do it the other way. All right, so in the ion party, all the ions are floating around in our ion party up here, and they are colliding with each other. At one point, the sodium and the chlorine ion collide together. But they collide, they say, hey, how's it going? But they re-separate because they don't actually really want to hang out with each other. Okay. They re-separate because sodium and chlorine ions, when they join together, they're soluble. Now, then the sodium moves on and it happens to collide with a nitrate. So the sodium and the nitrate collide in this ion party. They bump into each other. They kind of say, hey, how's it going? All right, sorry. So the sodium and the nitrate, they collide, they bump into each other at the party, but they're immediately like, I don't really want to hang out with you. And they re-separate because the sodium and nitrate together are soluble substance. But then the silver ion happens to collide with the chlorine ion. And they hit it off. They like each other, okay? And in fact, they stay together. They stay together because silver and chlorine are insoluble and they're going to form a precipitate. Now, if you were at a party and two people who did not come to the party together left together, you would probably have a reaction. Okay. Because the silver and chlorine come to the ion party together or come to the ion party separately, okay, we look up here. They come to the ion party separately, but they leave together as a solid precipitate. They're the ones that cause the reaction. Okay. Over here, the sodium and chlorine combine, but they don't have a reaction. The sodium and the nitrate collide, but they redissolve, so there is no reaction. But the silver and the chlorine collide. They stay together and they leave the ion party as a precipitate, causing a reaction. Okay, so just make sure you have that copied. Okay. All right. So we know now that all soluble compounds are going to dissociate into ions, into our ion party. So if we look at our balanced chemical equation for this double displacement reaction, sodium chloride aqueous plus silver nitrate aqueous makes sodium nitrate aqueous plus silver chloride solid. Anything that is aqueous, so anything that is soluble, all soluble compounds are going to dissociate. So this means that anything that is subscript AQ is going to dissolve. So what we're going to do is write out the equation showing that all of our ionic compounds that are soluble have dissociated or separated into the ions. So our sodium chloride aqueous becomes a sodium ion plus a chlorine ion. Now I want you to note that we're including the ionic charge for all of the ions and the subscript AQ to remind us that it's dissolved in water. If you don't remember the ionic charges, you can get that from your periodic table of complex ions. So our sodium chloride dissociates into a sodium ion and a chlorine ion. Our silver nitrate dissolves into or separates into a silver ion and a nitrate ion. Our sodium nitrate separates, it's an AQ, into a sodium ion and a nitrate ion. But our silver chloride here is a solid. It is insoluble. So it stays as solid sodium chloride. Remember silver chloride. Remember, the silver chloride left the ion party, the party of ions floating around in solution. It will not dissociate or separate into ions. When we write out and show our soluble ionic compounds separated into ions, we're showing the total ionic equation, or TIE. And what it does is it basically shows which ions are in a solution and which ions are found as a precipitate or as the solid. So just make sure you have that copied down. Okay. Now, if we look at our equation here, we can see that we have some ions that appear exactly the same on each side of the equation. We have a sodium ion in our reactants, and we have a sodium ion in our products. We have a nitrate ion in our reactants and a nitrate ion in our products. They appear exactly the same. These ions are called spectator ions. Now, our spectator ions, they are present during a reaction, but they do not participate in the reaction. So the sodium and the nitrate, they were at the ion party, but they didn't participate in the behavior that caused a reaction. They were there, but they didn't leave with someone else and cause a precipitate. So we call them a spectator, okay? Just like somebody sitting at an NHL hockey game in the stands. They're at the hockey game, but they're not playing the hockey game. They are spectating the hockey game. Okay, so the sodium, the nitrate, they are spectating the reaction. Because they're spectating the reaction, we can eliminate them. So we can cross them out, which is what I've done in yellow. The sodium and this sodium can be crossed out because it appears exactly the same. And this nitrate and this nitrate can be crossed out because they appear exactly the same in reactants and in products. And what we're left with are the ions responsible for the formation of the precipitate. So we're left with the chlorine ion and the silver ion, and they're making the silver chloride. We're only left with what was responsible for the reaction. Okay. So when we rewrite out our ions and show just the ions responsible for the reaction, like I've done here, This is called the net ionic equation, or we shorten it to Ni. And it only shows what is involved in the reaction. So I would hit pause and make sure that you have this copied down. All right, so we're going to do an example together where we have a double displacement reaction and we write out the total ionic equation and the net ionic equation. So if we look, you already have your double displacement reaction here. You have sodium sulfate aqueous plus calcium chloride aqueous reacting, that's what that means, to make solid calcium sulfate and aqueous sodium chloride. So we have to pull out all of the ions, write out all of the ions that would exist in the ion party. That's what the total ionic equation is. So our first ionic compound is, that was not what I wanted to do. Here we go, fix that up. Na2SO4. Now, so we know that this sodium sulfate is going to separate into a sodium ion. So Na, we include the ionic charge, and we write the subscript Aq. And it's going to break apart into a sulfate ion with its ionic charge plus Aq. Now, one thing I want to point out to you is that in this ionic equation, we have it's Na2SO4. Because what that's really saying is that if we were to draw the Lewis structure for this compound, it would look like this. Okay, there's 2 sodium ions in this compound. So we have to actually indicate that there are 2 sodiums. So we put a 2 in front. So we're saying that there are 2 sodium ions. And then the other thing I want to point out to you is that we can, in the ionic compound, it is a sulfate ion, and the sulfate stays intact as a sulfate here. So we can write it out as a sulfate. Okay, the sulfate is a polyatomic. So we'll just leave it as an SO4 2 negative instead of pulling it apart into a sulfur and an oxygen. Okay. So now we have to pull apart our calcium and our chloride into ions because it is calcium chloride aqueous right here. So aqueous means it's going to get pulled apart into its ions. So we get a calcium 2 plus Aq plus our chlorine, ionic charge 1 negative Aq. But again, something just to be mindful of is that we have a 2 right here. So this 2 is telling us that in this ionic compound, there is 1 calcium and 2 chlorines. So we have to put a 2 in front here. Okay. And I just realized that I did not balance this. So I'm going to quickly balance this. It's not a big problem because I haven't got to the point where it's important yet. But in order for this equation to be balanced, there needs to be a 2 here. In fact, you should always balance first. That is definitely my mistake. And I should have done that. Okay. So now we're going to look at what ions have come to the ion party and are still at the ion party. Our calcium sulfate, or CaSO4 solid, is not soluble. It is not Aq. So it stays like this. Okay. We cannot separate that because it is not soluble. It stays as a solid. But our last compound involved, our sodium chloride, is soluble. So we're going to separate it into our ions. And I'm running out of space, so I'm just going to write this on the bottom. But we have that 2. There is 2 sodium chlorides. So when 2 sodium chlorides break apart, we end up with 2 sodiums and 2 chlorines. Okay. So this is our total ionic equation. In order to get our net ionic equation, we are going to eliminate or scratch out our spectator ions. So you can cross out anything that appears in identically on both sides of the equation. So if I look, I have 2 sodium ions in my reactants, and I have 2 sodium ions in my products. I also have 2 chlorine ions in my reactants and 2 chlorine ions in my products. Another quick look is showing me that I've eliminated everything I can. And so what I have left is a sulfate and a calcium ion and a solid calcium sulfate. So those become our net ionic equation. They're what's involved in the reaction. So my habit is to write the metal first. I'm not going to penalize you too much if you write the nonmetal first. It's not really a big deal. Some teachers might care. I don't really. Okay. Great. So that is how you get a total ionic equation and a net ionic equation for a double displacement reaction. So what I'd like you to do now, after you have that, you've hit pause and copied that down, is see if you can get the total ionic equation and net ionic equation for this reaction in example number 3. And once you've tried it, hit unpause and check your work. All right, so there's the solution for the example number 3. Just really want to remind you that in order to get a level 4 on this, you have to include ionic charges for all of the ions, and you have to include subscripts for everything. So just really double check those ionic charges using your periodic table. Go through a little checkpoint that every single ion has its ionic charge, and every single substance in the balanced equation, the total ionic equation, and the net ionic equation has a subscript. Okay, so that's the end of this video. Make sure you do some practice on this, and we are going to use this learning in our next task.